All right. Hey, folks in SOC365. Sorry that we were unceremoniously interrupted by the fire drill earlier today, or the actual fire event ended fairly soon after I said that everyone could take off. So I didn't know that that would happen at the time, and I promised I didn't pull the fire alarm. So hope everyone had a nice time just hanging out. I will try to go through the lecture fairly quickly. For the people that weren't in class today, I guess you can probably infer we had a fire drill. It happened about halfway through class. I'll start from the top because in the process of all of that, the recording of the first part kind of got corrupted. So we're just going to go through it from the top. I also did discuss a couple of things that are a little bit technical, and I want to make it clear what's happening there. So I'm just logging on to the website. Obviously, you've done this part if you're this far. But we'll basically start from the top. Sorry for the delay here. I'm in Sewell on the 3rd floor, so my phone for Duo Mobile was a little bit slow. Okay, so obviously, just to reiterate, in case anyone doesn't know, totally fine if not, the slides can be found in the relevant week of the class. I'll click on Student View so you can see this on my screen just as you can see it at home. I put the lecture notes here. Today, these are a do file. There are some other announcements that I made about a couple of other topics that aren't in the do file, so I'll just briefly mention those. One, reading notes looked great. I would say, generally speaking, you don't need to be nearly as comprehensive as I am, so some people maybe erred a little bit too much in that direction. Just save yourself the time. On the other hand, some people sort of picked and chose what they wanted to comment on, which is good. These are meant to help you, but I would say in some cases, people were omitting like probably a little too much. So try to balance there. I give people credit for doing their best, but these are just sincere, friendly feedback. Exercise 1, I'm giving a 1-week amnesty on because some people had trouble with that. You can turn it in whatever you like. There's not any tricks to the assignment. I don't want to freak anyone out who's already done it. If you already did it and felt good about it, don't worry about it. Feel free to submit. But I do know it's a new part of the course. It can be challenging for some folks. So I want to give people that amnesty. I do tend to err too much in the direction of being generous with that stuff. So I have to say I won't do this in the future, but for the sake of letting people have a little bit more time to get used to Stata and that sort of thing, I will do that this time. So feel free to come ask me about that. But do ask me about that, especially if you're a person who requested an extension. Please do ask me about that. Okay, that's pretty much it. The other announcement was about the projects, and I'll actually pull that up at the very end. So let's pull up the do file. So go into downloads here. And actually what we want to do is move this into the correct folder. So we're going to do that here. So we'll go to downloads and we'll come here, move this to the desktop. And whoops, you can see I have added a couple of things to the desktop here. Close these. So probably the most efficient way, by the way, if you're just navigating on your computer and you're like looking at all the stuff on the desktop, generally speaking, this view right here that basically renders things as text or as icons, as Mac puts it, is best. There's a comparable thing on Windows too. I would say these other views here, like this folder view or this gallery view or whatever this is, I'm not actually sure, I guess like a weird preview thing, oftentimes aren't as useful. So I was just talking about that with someone after class today. Just a tip. Then you want to move this into the right folder here. And so we'll put this in the do file folder. And then we'll open it. Okay, we got a message about Stata being temporarily unavailable. We'll see if that becomes a problem later on. Probably not a big deal. Okay, so we started actually first by learning a new way to connect to directories, basically. And so last time you saw a little bit of this from me, the fact that you can use this tilde as a shortcut for the home directory. And there's also a way to do that in Windows. And in theory, it should be basically identical. But if you're using WinStat, there's a kind of tricky thing where WinStat, technically, basically these shortcuts get a little bit confusing when you have like a remote hard drive effectively, which is what's going on with WinStat, so to speak. And so some of these shortcuts aren't going to work as well. So I thought about it a little bit, and I remembered a somewhat obscure shortcut that I learned once before. This is really not that useful in practice if you're not constantly toggling between two different kinds of operating systems. But since I am doing that as the instructor here, and since I want to be a little more even-handed, I'm going to show it to you, and you may find it useful. So we're going to change the shortcut, or we're going to use the shortcut basically after setting a parent working directory. And the parent working directory for all things related to this course should just be the overall folder. So we're going to do that after we run our standard header here. Okay. And then what we want to do is go ahead and log this, and we're going to log it as a text file as we've been doing. So you can just write the text option here. And we're going to use the shortcut where we use the dot subfolder shortcut. Basically what that means is that now that we've changed the directory to this folder, we can access subfolders within it by doing this somewhat clunky thing, but it's really not that bad. You just write a period or a full stop or a dot, then /, then the name of the folder that you want to access. And here, remember that I can just make a new log file called lecture 3 by just typing it here. If I wanted to, well, you'll see later on how we can also pull data from subfolders like this. So the nice thing about this is if you are on Windows, all you need to do is get the correct parent directory from up here, or sorry, not from up here, you want to put it up here. You want to get it from up here by going into that folder and then clicking in the kind of address bar, copy file as text or something along those lines. Basically right click and then look for something that's like copy path as text or copy as text. Then paste that in here. Remember that you don't actually technically need the quotation marks because this is not a string and it doesn't include any strings, but it's just a good habit because sometimes you will have strings in there. So notice that I don't really need this. I think, yeah, last time in my appendix, I showed you what it looks like when you put a string in there and you do have spaces and you omit the quotation marks. It's not a good thing. So we'll put them back just as a matter of consistency. But so anyways, you want to get the correct folder, and then all of these other shortcuts don't need to be changed. And I tested that with WinStat on my own yesterday, and we confirmed this morning that it did work for most people. So that's a really nice thing because now you don't need to go back and change every one of these pathways. So just make sure you change this correct parent pathway. Again, it's a nice shortcut. You may not find it that useful in the future, but since we are working in this collective enterprise together, and we don't want to discriminate with respect to operating systems, this is probably the by far best way to do it. So make sure you can get to this place. And if you have a Mac, by the way, as long as you have this setup on your desktop, you have a folder called SOC365sp22, and you're putting stuff in a folder that exists called do, then you shouldn't need to change any of this. So it's only Mac folks that need to make the one change. And then we can get into the point of the lecture, which is exploring some basic techniques in data cleaning. And basically what we're going to be doing is looking at cases where we have implausible values in the data, whether they are implausible in a logical sense, whether they don't seem to correspond with the things we know to be true of the data set, like people are included who shouldn't be, even though those people could very well exist. But we'll also look at cases of people who probably can't exist, people who are 500 years old, people who are, again, 100 feet tall, repeating some of the examples I used in class, but that's the purpose of the lecture. Okay. So Mitchell, I do want to apologize a little bit. The text is maybe a little bit, well, probably a lot bit closed-minded with respect to the possibility, for instance, of men having children. I would say a correct analysis of gender means that that's perfectly possible, but I don't want to get into the weeds too much with that. The point he's trying to make, whatever his retrograde opinions on gender are, is correct, that there's a lot of different ways in which data can seem to be mistaken, and we want to be subtle and flexible in our analyses thereof. We start with looking at double data entry as a way to capture basically errors that might have existed, however, that are even simpler. And those are basically just literal data entry errors. We won't do a lot of direct data entry in this course, although I'm going to have you do some this week for your exercise. But it's not a bad thing to know. And basically, I want to show you how you can use Stata to look for that kind of error. So I'm going to introduce such an error by construction and then show you how to look for it. So we get our first test of how to use this shortcut here. And if we run this, we actually can pull up the dentist data set. I'm going to make this a little smaller. This was set really large last time because I was directly connecting to the projector with this. But in general, you should make this window smaller than I had it. To do that, you just need to use the standard shortcuts for magnifying things, which will vary between Windows and Mac. On Windows, it's Command minus sign. On Mac, it's Command minus sign. On Windows, I'm not sure off the top of my head. I have it in muscle memory, but I'm assuming probably folks know how to do that. Okay, so we use this data set, and we're going to make an ID variable on Stata. You might notice if we just describe the data set, we don't have such a variable. We just have name, years, full-time, and reccom, or recommendation for plot income, and remember I just typed desk for that. We reviewed this in class, but in general, in Stata, you can abbreviate things up to the point where they become ambiguous, and then you can't anymore. So sometimes you can be really minimal, like I can write some years D. D stands for detail. I'll just briefly illustrate that. This gives the same results. See, D here is unambiguous enough that you can just simply abbreviate it, or D is unambiguous enough that you can abbreviate detail in that way. Okay, so let's come back to the main point here. I'm going to try to go faster and have fewer detours in this lecture, although a lot of these detours are, I think, useful review for folk. So we want to make an ID variable, and then we want to basically drop some cases and show how we can tell Stata to look and see, did we maybe miss someone? So if you do have ID variables assigned to every subject, and they're assigned in some rational way, such as the total number of ID variables is basically like the highest ID given in the data set is the number of ID variables you have. So if you have 560 people, the nth ID is 560, and all other IDs are only the numbers 1 through 559 inclusive, that sort of a thing. If you do it like that, then Stata can help you out and see if you maybe missed someone, or you possibly double counting people. So we're going to generate this ID here. We're going to call it seek ID, seek for sequence, and we just write it like this. And you can see we now have this new variable, and we can, let's just say sum ID, and there's 5 observations, min, max, 1, and 5. The mean and the standard deviation here obviously are not, especially meaningful, but that's okay. We can sort the data by this variable. So let's show what it looks like first. We'll just list everyone, and they're listed in this way. So Don, Olive, Isaac, Ruth, Mike. Let's sort by sequence ID. And then we can just come back and list these again. And notice how I'm using the command window to basically just enter things that I might have forgotten or I want to just show briefly. You can see that it actually doesn't change the order here because Stata just assigned the numbers to the people in the order that it found them. But now if we try something like sort name, oh, sorry, these are already, going to be, listed in a different order here. So basically, if we sort by name and then go ahead and list them again, we get this alternative order here, but we could resort them in this case just by writing sort seek ID and then list, and you can see they're now back in that sequence order here. Okay, now let's simulate what would happen if we had missed one. So let's say we missed Ruth. And I made a big to-do about this in lecture because it's kind of important. There's two things to watch out for here when you drop this person. One, the name double equals right here is the correct way to say drop if the name is exactly equal to this value. I didn't show this in class, but let me show what would happen if I tried to drop someone without that. So we dropped Ruth correctly, but let's see, what if we try drop if name equals Y, Don, you floss more, and we get a mistake. And there's actually a couple of mistakes here. So the first is that we don't have the double equal sign, because in Stata and most programming languages, one equal sign means assignment. And what we mean by assignment is that we are trying to tell the computer in the future, like let's take a concrete example. Let's say we're making a new variable. If we say gen new var equals something, we use one equal sign. And what that means is we're telling Stata, make a new variable that takes on values according to this rule. And the equal sign sort of stands in for according to this rule. Double equal sign, by contrast, means that we are telling Stata to evaluate whether some condition is true or not, basically. So we call that evaluation. So let's see if that fixes the problem. Nope, it does not fix the problem. Why not? Well, we also have a string here. Name is a bunch of English language words here. Why, Dawn, and you floss more. And notice that, well, you can't really see this, but what Stata is doing is trying to evaluate why on its own. It thinks we've put 3 discrete terms in here, and it doesn't really know how to evaluate them. So we need to put quotation marks around it, and now we can actually drop Dawn as well. And we're actually going to have a slightly different setup here than in the book, so let me just rerun this stuff. And by the way, if you ever make a change and you're like, shit, I didn't mean to do that, I wanted to follow the do file a little more exactly, you can just always rerun stuff. So here, I'm just going to reload the data set and hit clear. And if I list everyone, everyone is still in there. So that's a helpful tip too, I think. So let's go back to the main thread here. So this is the correct syntax. You need to have double equal sign and the quotation marks. Let's go ahead and do as we intended and drop Ruth. And we can list and see what that looks like. And you can see that we have omitted Ruth from the set. She was observation 4. Now Mike is the 4th observation, although he's 5th in the sequence. And we can see that Stata actually knows how to tell us, well, if we program it very precisely, it can tell us that we have precisely that kind of a mistake. There's an error here, sorry, that's embarrassing. So basically I walked through this in class, it's a little bit complicated, but if we run this command, we can basically identify people who are not n+1 with their sequence ID, where n just means the current number of persons. It's a little confusing. Probably should be something like j+1, but that's just how Stata works. So basically what we're doing is saying, tell us, Stata, if you find someone whose identification number, identification value on that variable is not the person right in front of them once they've been correctly sorted, +1, basically. And that, in theory, should happen if we, as I said before, put the ID numbers on people rationally. So let's try that. And what this code means, by the way, this says list the person's sequence ID if it is the case that their sequence ID does not equal, so tilde equals sign and exclamation mark equals sign would also give the same thing. I can just briefly show that. These are identical. It's really an aesthetic choice. Gives the same thing. Is not equal to, and then this expression is a little complicated, but it basically means what I said before, the person right in front of them, their ID number +1, and then we just say look in 2 to L, which basically means look in observation 2 onto the end. In general, tilde and exclamation mark both mean not in Stata and in most programming languages. Okay, so here we found the error that we introduced. We can also look at how we might compare 2 separately entered data sets that exist in our DMUS data. So here we want to use this survey 1 data, and it looks a little different to the book, but that's because the book has 2 editions. We're using the first edition, and I think the authors slightly changed some of the data sets, clearly not very much, but some of them look a little different. It's not a big deal though, and if there's ever an important distinction, I'll let you know. But generally speaking, Stata Corp, which produces the book, knows better than to do that. It's a pretty big computing no-no. So let's go ahead and basically load this first iteration of this survey. And then we're going to sort by the ID variable and then save. And it's rare to save data and just replace under the original name like this. So why are we allowed to do that? Well, we're just reordering the data, not really changing them, so it's not such a big deal. We can always undo that, basically. Whoops, and sorry, this computer's a little glitchy. So we went ahead and sorted, and then we saved the data. And you can see I did this several times because I accidentally double-clicked, kind of got this hair trigger mouse here. Okay, now let's do the same thing for the second iteration of this survey. And then what we can do is see if they match. And you can see the IDs match. So basically, these 2 data sets have the same set of IDs in them, and they have both been entered correctly. But we can see what will happen if we go ahead and drop one of the people. So here I can list the IDs, and there's 8 people in the set. So let's just say I arbitrarily drop person 5. And we can list again, whoops. Oops, I need to, this is gonna list every variable, which is a little bit annoying. So we'll just write list ID. And you can see here that I dropped person 5. So ID 6 is listed as the 5th observation, and ID 8 is listed as the 7th, and so on. So now let's go ahead, and in some versions of Stata, you'll get an error message when you run this, which is why I've left it as a comment, but we can just take it out of comment mode by deleting the comment notation and run it. And that's often really helpful if you have something that you think might work, but you're not totally sure. Just put it as a comment and say the user can run this as a comment if they wish, or a command, pardon me. So in this case, it doesn't actually yield an error message, but we get this note that the master data set has 7 observations, but the other one that we're using has 8. Okay, so basically we just found that we made the mistake that we did intentionally. Now what will we do here? Well, in this case, I obviously made the error on purpose, so I should just have not done that. But you know, if you had an actual data set, this is where it gets a little tricky. I think it was Genevieve who made this point in class. There's quite a bit of discussion in the book about going back to the code book. And so what you want to do in these circumstances is get really familiar with that code book, get to know the data set, look and see who compiled it, why they compiled it. And you want to just think about what kind of mistakes may have been likely to have been made depending on the circumstance. Were there a lot of, you know, I'll be honest, academia sometimes relies on low-wage labor, for instance, people that may not have much skin in the game, so to speak. I actually was worked a little while for a data entry farm, and have done plenty of manual data entry for no pay as a volunteer in the labor movement. And sometimes, you know, you're already volunteering your time, you're working hard for the sake of the cause, and you might be, you know, you're not going to be fired. So, you know, you might be a little bit more prone to just making a goof here and there. That's something to consider. Like, is there that kind of data likely to be error likely to be present? In other cases, like with the GSS, for instance, or the CPS, that may be less likely because you typically have professional bureaucrats whose job it is to do this, checking all that stuff. On the other hand, they might have missed other kinds of mistakes, and that's actually kind of what we're going to turn to now. And these are things that those sorts of people actually really can't fix, but they, so it's not like their fault or something, but we need to be cognizant of it. What am I talking about? I'm talking about unlikely values. So let's go ahead and check out individual variables and look and try to see if we can find any implausible values of variables. So let's start here. And we're going to look at these data from the Working Women Survey. And I showed in class how to make sure you have these data correctly loaded into your relevant folders. If you don't, probably in order to save some time that I chewed up in class with this, which is, I'm really happy to get everyone on the same page, but because those errors tend to be kind of individually specific, I would say try to run lecture 2 again. If that doesn't fix it, come see me. But I think everyone is more or less on the same page here. If not, totally fine. But that's often a thing that's just easier to handle individually. So we've loaded the Working Women Survey. And let's look at these 2 variables that the book suggests we look at: call grad, whether or not someone's a college grad, and race. And we're putting missing here to tell Stata to show us any missing values. It's actually not very informative here because we don't have a ton of missing values here. We'll see some examples later on. But these look like they kind of check out. They're qualitative variables, so we can just use tab. I showed in class that if we use tab on some other variables, that's actually a pretty bad idea. We'll see that in a moment. So continuous variables, for instance, that have many possible values, tab is usually pretty uninformative. But, you know, the book kind of foreshadows that race actually here should not have a value larger than 3 or less than 1. So we'll check that out in a little bit. And this dummy variable, the call grad variable, I'll explain dummy variables later on, shouldn't take on a value that's, you know, not 0 or 1. And it seems to be okay there too. So we're doing fine so far. We'll come back and look at some problems with those variables later. But let's come to a bit of a subtler problem. So what if we encounter values that seem implausible, but that aren't technically disallowed? So we could look at unemployment insurance. And we see here that the book suggests that UI might be capped at $300. And we see that there's nothing above $300. So that doesn't look like too much of a problem. You want to call attention to two things. One, again, we can abbreviate commands, as I mentioned before. The second is that this would be a case where tabbing it would not be very informative because there's a whole lot of possible values. And we see, in some cases, it'll take up all of the results window. Here it doesn't, but it still is kind of an eyesore. So we probably don't want to run tab. Running sum is a much better idea. Now, this is a slight mistake in my comment here. We actually want to look at wage here to find some really atypical values. So let's look at wage, and I'll upload this corrected version of the do file in a second. So if we do this, let me add one command here. Let's simulate what it would be like to just notice this. So let's do sum wage, and then let's run some of the commands that produce nice graphs that can also show us this sort of thing. So in class, Rob helped us out, graph box, which is a good way to do this. So just pulling up a box plot. Histograms also are pretty nice for wages, or well, for any continuous variable really, where we want to look at the distribution. And we're actually going to run these one at a time. If you run two graph commands in a row, Stata will delete the first one and only show the most recent, unless you do some special coding. So it's usually a good idea to run those one at a time. So as we saw in class, the box plot method produces this really, horrible looking graph where the box is basically not visible and there's just a single line. So that means we have some pretty extreme outliers. Again, it doesn't force on us the conclusion that these are impossible values, as I mentioned several times in class. The two key rule is basically an attempt to parameterize a distribution, or in other words, specify a particular form of the distribution that seems implausible, but that's not the same thing as saying, yeah, this is just obviously BS. So we need to use some other context clues. Basically, the two key rule, which you can effectively think of as being shown by this box plot. So it's showing you these individual dots here are ones which are outside of basically the IQR multiplied by 1.5, arbitrary constant, added to the third quartile or subtracted from the first quartile. Again, you don't have to know that. It basically shows us as observations, but we might still think those are fine observations, right? They might just be outliers. So we still want to think about maybe dropping them depending on what kinds of commands we want to run and that sort of thing. But we shouldn't just delete them because they're not obviously data errors. So we can also look at a histogram too. You'll see the histogram also shows pretty clear evidence. It's hard to really see here, but if you look right in this area, there's a little bit of yellow, and right over here, a little bit of yellow, indicating that there are some observations way out here. Even if it's hard to see, Stata is extending this x-axis for that reason. So that means we, just have some really large values of wage. We can list the ID code, and we can list the wage, and we can see, if first of all, how large these are. So $380,000 per hour is pretty obscene. I jokingly said in class that Jeff Bezos might make that much money. That I think is probably even more than he makes, although possibly not. Maybe someone can look that up for us. It's obscene whatever it is, but it may not even be this much. Case in point, how likely are you to get Mr. Bezos or Mr. Gates in your sample, right? Not super likely. It's possible, although there's actually a well-known fact that a lot of those kind of the uppermost echelon of the bourgeoisie tends not to answer surveys, which is an interesting problem for inequality researchers. At any rate, pretty low probability that you're going to get those guys in the sample, even if they do answer those questions. So, you got to go check the code book and see, like, there might be some other indications. One thing you could do, for instance, I don't think we have information. Also, this is a Webman data set, so this would have to be Mackenzie Scott, Bezos's former wife, would probably be the person. Actually, I don't know. Another interesting thing to look up: who is the highest net worth woman in the United States? At any rate, you would, need to figure out, like, is it even remotely possible? You saw in here, I just put in home. You could put in a check, like, how many homes does this person own? If they put down they own 30 homes, you may have just gotten a really wealthy person in there. But you have to use some, other checks and controls. So that's kind of all we can really say. We can see, and I'll show this later on, that you can always just run conditional commands without these people included, which is a bit of a pain, but it might not be a bad idea. It's a way to allow you to check your results really quickly against what would happen if you did include the extreme outliers. The book shows that you can do this also with age. This is a little bit tedious, but the point that the book wants to make here, which is not a bad one, is that in this case, it's really implausible for a woman or any person to be 45 years or older, obviously. But why is it that these values seem unlikely here? Well, it's because we might know, for instance, from the code book or from just the name of the data set or whatever, that this is a survey actually of people who are younger than 40, for instance. And then we want to be careful about this. Okay, this is where we kind of left off with the fire drill. So let's go ahead and also examine some implausible values on the CPS, the current population survey, which is in very common use and is a very nice data set with really high quality income data. So let's make sure we've pulled this up. If you haven't downloaded this, you can get it from the course website. And you can go here. So far we've been using book data, but all the other data basically live here. This is a really big folder, so you may want to download, you can very likely download it unless you have a ton of music or video on your computer, which you might. So then you want to be a little bit careful because there's, I think it's the IPM's data. We scroll down a little bit, that, yeah, it's almost a full gig. But you can just download things individually too. So here, so far for this lecture, we're just going to use these two data sets that I often use for examples, the GSS 2018, and then the CPS 2019. Oops. So those are, you can just manually download those, and you want to download, show this really quickly. It'll be in your downloads folder. So you want to come here, and basically you can do a couple of different things. You can copy it, but you can also just drag and drop. So here, then come, whoops, that's just going to open it. Sorry, folks, double clicked on accident. But you would want to come here and put it in original data, and then you can say I already have a duplicate, so I'll just stop so we don't cause any problems here. Okay, so we're going to use this. And we'll come back to the window here. And so we also might want to look at, for instance, the possibility that people are working unusual hours every week. So maybe you know from history that it's unlikely that people work more than 12 hours a day, 7 days a week. Even that is extreme, although it's certainly possible that it happened, because it did happen in many places. 6 hours a day was more likely. So we might want to say that's our cutoff for the likely number of hours of work a week someone could engage in. And I didn't really show this. I just kind of said, there's too many, there's people that work more hours than that in the data set, but you can look and see here. We can look at an example here, and in class, I had a brief moment of confusion because I wasn't sure why this wasn't working, but I forgot that this is a giant data set. So it's going to take a little while to run certain commands. You can see here it's still working. The computer I was on did not show this icon, so sometimes that can be a little bit alarming, but just know that Stata is working in the background. And this will take a little bit of time, but that's okay. By the way, we can see how many people are in the data set. Some people in class gave us some really nice hints on that, which is a part of your first exercise. I'll describe those briefly while we wait. So Rob suggested one method, which is to find the unique ID variable and summarize it. This probably won't run until the box plot comes up, but that would be one way. We'll run that in just a moment. And then Maggie also suggested just writing describe, and we'll look at that in a moment too. This is going unusually slow here. Yeah, it's one way you can tell that there might be a problem with the data is that just takes a really long time to run certain graphs. There are a ton of observations, but it can be harder on the computer when they have like really, basically the computer needs to make an unusual kind of graph just to show things correctly. So. Okay, so you can see that took a little bit of time here to pull up, but this is a pretty extreme circumstance. We'll oftentimes not work with data sets that are quite this large, but we can see some obvious outliers here, of course, and some of these seem really extreme to the point that we don't even have that many hours, basically a day in a week. If you multiply 24 by 7, you can do it mentally. Let me just show briefly, though. You can also do that in Stata. So you can use Stata as a big calculator if you like, and the way you do that is write display, and then just you can type this in like you would type it into Google. So 24 by 7. We're going to go 168 here. Pardon me. And so obviously some of the numbers in this graph exceed that value or are very close to that value. And so we know that we have some obvious errors here. We could also pull up a histogram. I'm not going to do that because this went especially slowly on my computer. It'll probably go faster on yours. Yeah, we obviously have some issues here. So to see that number of observations, by the way, that's kind of causing the issue, let me show Rob's suggestion. So some unique ID. And we can see here we've got about almost 300,000 observations. And you can see we've got these numbered in a pretty nice fashion as well. The mean and the standard deviation don't mean much. And we can also just use Maggie's suggestion to just describe all the variables. Fortunately, there's not a ton of variables in the CPS. There's a lot, but we didn't have to scroll very far. And we can see the total number of observations here, tolerable number of variables. A lot of these, by the way, are like legacy things that are, you can see things are asked in the same way many different times, and we don't have to worry about all of those. Okay. So now what we want to do is find a way to quickly get a sense of like which values we want to omit. And something that's oftentimes useful in Stata is to define a scalar. And a scalar, remember, is basically a word for just some real number. And its use comes from linear algebra, where we're oftentimes working with vectors. In fact, basically by definition, working with vectors and matrices. You can think about a vector. I mean, you probably learned in high school physics that it basically is a magnitude in a direction. So it can be represented as a point in 2, 3, or n-dimensional space. But it also is just a list of numbers. It can be listed as a row or a column. So you can have a column or a row vector. And you also have matrices. And matrices are just basically a table that's got both columns and rows. So a vector is like a one-dimensional matrix of some kind. And a matrix, you can just think about as the familiar spreadsheet that you use in Excel, or if we pull up Stata, its matrix here, this is the matrix of data right here. So we call scalars by contrast just to mean real numbers. So what's the use of this? Well, a lot of times, like the really convenient thing in Stata, well, just in general with like the foundation of statistics, is being able to use names for variables so that we can say all of these numbers that all these people have are conceptually the same thing. Like the number for you and for me and for person X, those are all measurements of education, right? So variables are really like a key concept of statistics, really, with a name for convenience. So we can do that, and that's what a scalar does. So here I'm going to define the scalar likely max hours as basically just the number of possible hours that I think is probable, and it's still pretty large, but I'm not making it the physiological maximum here just for the sake of keeping things open. We'll do that in a second, actually. So you might notice I don't even need to actually write down the number 84 here. I can just tell Stata to compute it for me. So I can say define scalar, and you just write that as scalar, and the name equals this. So let's do that. And now I can tell Stata to display the scalar. So di, that's sufficient to identify display, gives 84. So now I can go ahead and tab the hours last week if those exceed the likely max hours. And again, I just picked 12 by 7 because 12 hours a day seems like the maximum, the maximum that someone could possibly work, and even that is really extreme, and then 7 days in a week. So there's quite a few people that appear to be working above this, and there's 659 observations, which isn't really extreme in the case of 300,000, but it's worth noting. And this seems like sort of unlikely. Notice that we could also go a little bit further. Sorry, again, I have this really glitchy mouse on this computer. We could go a little bit further and only define a scalar for the maximum hours a week that are physiologically possible if we want to be a little more conservative. So let's do that here. And notice that there's still 47 observations. In this case, I figured that people need to sleep at least 8 hours a day, right? So this is extremely unlikely that anyone could work 16 hours a day, but let's just make that our cutoff. And again, you can see that Stata will return this value. So we should get 112 when we DI max weekly hours. And we do get 112. These are people that are, clearly some kind of data error. We might want to look at basically like what happens if we include them. So first of all, we can just show scatter plot with a regression line. This has a sort of subterranean purpose of me reminding you that Stata can do cool stuff too, just so you have some motivation. This is going to go a lot faster than the box plot because the outlier problem is not going to be quite as extreme. So I shouldn't need to cut here. We'll see though. Stata's working hard here, so it showed us a brief preview, but then it cut back, but we'll see if it can handle this. Yep. So it's got to show quite a bit of, extra space on the x and y axes here because of these extreme observations, but we see more or less almost like a 45 degree line here. So yeah, pretty straightforward regression line. Let's see if we can show what this looks like with these observations dropped and see if it appears to change the slope or the intercept too much. Then I'll show how to compare them numerically. So notice the way that I did this is I just wrote this command if hours last week is less than likely max hours. And this really doesn't look that different, right? The slope of the line didn't change direction. It didn't even appear to change magnitude that much. The intercept appears to be nearly identical. So it doesn't look like this is making a huge difference, in part because it's a small number of observations, but it's still worth noting. So we can go ahead and quantify that difference. Again, you can see how to use conditional commands here. Again, this is kind of a pain to do too often until you learn programming, but it's probably the best way to do it, rather than saving 2 data sets and like going back and forth between 2 Stata windows to compare. So I think using conditional commands to check differences between results with and without outliers dropped is the best way to proceed until you are sure you want to drop them. So we can show the summary statistics and look at the differences. And notice that the summary stats really aren't that different. The mean doesn't even change by, actually with rounding, it doesn't even change by a single hour. Obviously the max is much smaller when we drop people that are exceeding the likely max hours. Now, if we dropped all people that are like above, I would doubt many people work beyond 60 hours a week. That's just my personal, being a member of the labor movement for a long time and knowing a little bit about labor law, I'm guessing that this is probably the true maximum. And we can see, okay, so this actually does seem to make a pretty significant difference because there's, a little more than 10,000 people that work between 60 and 83 hours a week, according to the CPS. This is probably more sage to do, but again, we would want to be much more explicit about what we're doing here if we were doing an actual analysis. So just want to show you it can make a difference. The more outliers you drop, the more difference it tends to make. Yeah, it's just something to consider. Okay, so we can also look at the difference between the regression output here, and we can see here that the coefficient changes a little bit, not by a huge amount. The statistical significance, obviously in both cases, we have a pretty unrealistic null of no relationship between hours worked last week and your weekly pay. Obviously, those 2 things are related, so we're obviously going to reject the null of no relationship between the 2, i.e. the null that our population regression slope is 0. The strength of the rejection increases marginally. Basically, the t statistic gets a little bit larger when we drop the outliers, which sort of makes sense because those people who are working 200 hours a week probably were not also making the most amount of money every week because they're probably just outright data errors. We can see that the model fit improves marginally. So that means that in a bivariate case, that means by definition the correlation improved a little bit as well. But there's not a huge difference. The intercept actually does change significantly though, although the intercept is typically not substantively meaningful in a lot of sociological regressions because usually if you work 0 hours a week, you're probably retired, and the concept of weekly pay, you might have a weekly income. In fact, you very likely do, but it's not really pay in the sense that a pension or some kind of retirement trust isn't exactly speaking paid labor. So it's really deferred compensation from past labor. So that doesn't make a huge difference. But the point is there is some difference, right? And the difference could be more extreme. And I just want to show you on a real data set that's very useful and in high use, you can find all these kinds of unclean data. Sorry, I'm trying to make this a little bit smaller here. So, guys, acting up a little bit right now. Okay. The better mouse, I just left it at home. Okay, so we've run all this. So we could go ahead and drop these people if we wanted. And I want to show a quick little instructive moment here. You can see I have my slightly naive tone of voice here. Oh no, we dropped a whole bunch of people. What went wrong? Well, what went wrong? Turns out that hours are a missing variable for a lot of people. And so we actually only dropped, we dropped everyone that was just missing as well, because for whatever reason, hours last week, it's coded as a missing value by Stata. We can actually show that. So let's write tab hours last week missing. It's going to show a lot of people. Oh, we already did the dropping. Sorry, we'll need to do this first. So we'll reload the data set. And then we'll, this will be instructive. Let's check our working directory. Okay, and the working directory got changed to the desktop by mistake, probably because I accidentally double-clicked on that data set when I was messing around with the downloads. This is instructive. So anytime you have a broken path like this, you want to see what is my actual working directory. So now this is pretty simple. I just need to go back, and I don't even need to retype. I'm just going to change the directory here again. Now I'm back in the correct parent directory. I can confirm quickly with pwd, and then this will work again. And so it does. So an instructive moment, I made a similar goof like that in class. I'm not doing that just as like some kind of gag. It's a common thing that happens when you're actually coding in real life. And you just want to do some troubleshooting. That's an interesting fact about coding in general, is that even, I was going to say even the greats, I'm not one of the greats, but even people that know what they're doing make mistakes all the time, because it's just an iterative process in a way that pure math or like pure sociology really aren't. So you'll get bugs all the time. Debugging is an art in programming. So you'll see me make mistakes like that, hopefully not terribly often, but once in a while. And if I never showed it to you, I would be telling you a lie. So it's good to see it once in a while. So I want to give you a sense of how to troubleshoot as well. Okay, let's come back to the main point. So I was going to show you what it looked like with missing values. And you can see these missing values are coded as a dot. So that means they're going to be omitted from most Stata analyses, which is good. But sometimes Stata will believe this number, depending on the type of function we're running, to be a very large number, actually. Summary statistics, fortunately, but for other purposes. So we need to just use this conditional here, drop if hours last week exceeds max weekly hours and is not missing. And that's how we write that here. This missing function is kind of special, so just copy the syntax. Remember that you can stack conditions by writing and. So now we should just drop 47 people, as we saw before, 47. We scroll all the way back up. It may not still be in the command window, but I think it is actually. Or the results window, pardon me. If we scroll down and find that output from before, we saw, 47 people up here. Okay, that all checks out. And I'm going to pause here because office hours will start. But at this point, I wanted to introduce, again, dummy variables because these are going to become important for the rest of the lecture. So I'm going to show you my lecture from last semester on dummy variables. For those of you who have taken 360 with me, depending on when you took it, some of you took it with me last semester, some of you took it with me a couple of semesters prior, and I played slightly different roles in those courses. I'm really keen on introducing this stuff early. Other instructors are not as keen on it. It's totally fine. It's just a principal difference in terms of pedagogy. So some of you are going to be really familiar with this. Some of you may not be at all. One reason I do tend to introduce this early on is because a lot of people think of it as a very advanced technique. It's really not. That's just kind of the holdover from how it's been taught in the past. But this is one of those things that becomes important very early on in your sociological programming careers, and really just in any kind of data analysis. If you were to go out and get a data analysis job in the private sector today, you would encounter it day one. I could almost guarantee it. So we do need to introduce that pretty early. I will assume no prior knowledge. So you can load this lecture. The URL was massive for the actual file, so I put it in a tiny URL, and then I just use this command here that lets you load websites from within Stata. So this will open it in whatever our default browser is. In this case, it's going to go to Chrome. And it pulls up, well, the Chrome default page, but it also pulls up this lecture right here. And so we'll examine that when the lecture resumes. And yeah, I guess this is relatively short, so we'll go over this in just a moment.